Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy, and we are in Digital Logic Design DLD lecture number 2501. We continue in a more advanced and more practical circuits in the synchronous sequential circuits. So as we indicated in the last lecture, we have four components for synchronous sequential circuits. We have the circuit diagram. From the circuit diagram, we want to derive the state equations. From the state equations, we want to build state table. From the state table, we want to get the state diagram, which actually completes the analysis. So we are in the analysis flow. Okay. Synchronous sequential circuits analysis and design are a little bit tougher than the combinational circuits. Why? Because I have here different types of inputs, different types of outputs, and it's a little bit confusing. However, the methodology that we will explain here in this lecture will make the analysis is very simple and without any doubts. So as we indicated in the last lecture, in order to successfully do the analysis, I want to do input-output analysis for my circuit. So in the circuit, I want to identify if I have state inputs and how many, external inputs and how many, which are the state outputs, and also the external outputs, if any. This is my first step. So by looking into the circuit, I can simply identify these different components. The rule of thumb for the number of state inputs is number of state inputs equals to the number of PPs. Golden rule. Number of state inputs, which are also state outputs, equals to number of PPs. How many PP in this circuit? This circuit actually contains only 1D flip-flop, 1D PP here. That means the input states are just Q. Accordingly, I have also one state output, which is the output in the future, Q, T plus 1. Next, external. Do I have external inputs? Yes, in this circuit, I have two external inputs. They are called J and K. In that circuit, I do not have any external outputs, so we will demonstrate the external outputs in a following example. If I have none. After doing this, I want to analyze the circuit. Analyzing the circuit looks to be complicated. Why? Because I have feedback. Remember that these are sequential circuits. So the output is also an input. Whether it is shown or not. The DVV, it wasn't shown because it's inside. It's a circuit. But here it is explicit. We can see that this Q is connected to the feedback. This Q bar is connected to the feedback. So this makes a little bit of confusion for the students. Don't worry. The methodology that we will describe right now is so simple, so easy, so you can analyze any sequential circuit without any worries. Okay? All what you have to do is that to understand that the outputs from the features is connected back to the inputs of the feature. And we agree that those are actually inputs to the circuit. We call them state inputs. So Q that is connected to the feedback here is simply an input. I mean this Q. And the Q bar also is an input. This is one other thing. Okay? So you don't have to worry about the feedback. Just break the feedback as if you break the feedback, as if there is no feedback. Okay? Fine. How can I analyze this? This looks complex. It's not that complex. My recommendation, it's a methodology that I always use, and the students find it very easy and very, okay? So the recommendation is, in order to analyze synchronous sequential circuits that has mix of components, as you can see here, you have some combinational components, ands and ors, and you have sequential, the flip-flop, okay? So my recommendation is split the circuit into two parts, okay? So actually, I can draw this virtual line here. This virtual line that I just drawn is actually separating the circuit into two pieces. This part here is the combinational side of my circuit. This part here is actually contains only sequential circuit, which is the physics. Agree? Now, since I split the circuit, forget about the feedback, analyze the combination alone, analyze the sequential alone, and you can easily drive the equations and just substitute those equations from each other. You will get your first output or the first requirement, which is the equation. If the first I have here mean I have item number one, اللي هو mean the circuit. I have the circuit. I have the circuit. Item number two is the equations. I am looking for the state equations. So as we recommend, this is the combinational part. This is the sequential part. We will analyze each of those components alone. Can I analyze the combinational part? The answer is yes. Okay. Can I identify the inputs and the outputs for the combinational? The inputs for the combinational, and the inputs for the combinational are J, K, Q, and the Q bar. We know that Q bar is the complement of Q. So actually I have three inputs. Right. What are the outputs of the combinational part? The output of the combinational is the interface between the combinational and sequential, which is simply the variable D. D is an output from combinational and it's an input for the sequential. Yeah, but this is the output. Can I analyze this? Yes. Fine. What about the sequential? Sequential has input D. Sorry, the output of the sequential is the output in the future. It's not Q. It is Q of T plus 1. By the way, analysis for sequential part is piece of cake. Why? Because there is no analysis that you want to do for the sequential part. The characteristic equation actually describes how this works. Q of T plus 1 equals to D by definition. If I'm done with the analysis for sequential part. What's left for me is the analysis for this. Analysis for this, you are clever in that even from chapter 2. Okay, can I analyze this? Yes. I have here D as an output equals to and or between two things. The first thing here is J ended with Q bar, ORed with K and K bar ended with Q. Done. Done deal. I drive equation between the outputs and the inputs of the outputs and the inputs of the combinational circuit, which is the analysis for the combination. I have the equation, the characteristic equation for the sequential part. So all what I have to do is to do simply substitution. The state output, the state equations is simply Q of T plus 1, which equals to D equals to J Q bar or K bar Q. I am done with the equation. I drive the state equation. Next, state table is the state table. Okay. Now, how can I build the state table? Okay, the state table as we learned in the last lecture. In order to get the state table, I have to show a table that actually show two parts. ايه هما التو parts دول؟ inputs واوتبوتس. الانبوتس let me just draw it. Draw it where? Let me just write the equation here, or okay. Let me draw it here. It will be congested. Let me draw it here. Okay. So let me take that big size. Now I have input, I have output, and as we agree from this table, I can identify two types of inputs. What are the two types of inputs? The two types of inputs are simply, the two types of inputs are the external inputs. I have the present state. For the outputs, do I have any external? No, so I have only the next state. Okay. External inputs are two columns. I have J and K. For the present state, I have only Q. Here I map those here. And for the next state, I have only Q, T plus 1. This is now TT. How many rows for that TT? 3 inputs total. So I have to draw here 8 different rows. Eight different rows. Can I fill in this TT? Yes. 3 inputs. My recommendation is always put the external, then the present state. It makes it easier as we 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Now we have the state equation through which we can write the state table. So here, if I put Q equals to 0, means this is nullified. So when Q equals to 0, the equation of Q plus 1 is simply J. Q0 means J. J means 0, 0, 1, 1. When Q equals to 1, this equation will be simply Q of T plus 1 equals to K bar. So K bar means 1, 0, 1, 0. I am done with the second component, which we call it the third component, which is called the state table. يبقى we got the state equation, we get the state table, and what's left for us is the state diagram. Okay, state diagram. Can I draw the state diagram? The answer is yes. يبقى 3 هنا ايه او 4. Component number 4 is the state diagram. State diagram, we learn how to build the state diagram from the last lecture. State diagram contains number of circles, number of arrows. The number of circles equals 2 to the power number of fifis. How many fifi in this circuit? I have only one fifi, so that means I have 2 states, 2 circles. One for Q equals to 0 and the other for Q equal to 1. The ordering of the external inputs and the present state will make the process very simple. Okay, now I have each circle, okay, has its set of rows. How many rows going out from each circle? How many state transitions going out from each circle? A golden rule بتقول 2 to the power number of external inputs. How many external inputs here? I have 2. That's why I have here 4 different arrows will go out from each circle. So for the circle number 1, we have state 0. Okay, the first arrow is for J and K equals to 0s. If I'm in state Q0 and J and K both equals to 0s, what will be my next state? I have to stay in the state. So actually, this arrow will send me back to the state. This arrow for J, K equals to 0, 0. Yet a 0, arrow for 0, 0. Agree? Make sense? Next, I am in Q0 and JK equals to 0, 1. Still, I have to stay in my state. Yet second arrow here is JK 0, 1. Next, I am in state 0 and JK equals to 1, 0. Where should I go? I have to go to the other state. This arrow for 0, 1 should go to state 1. Last one here is for when I am 0 and JK equals to 1, I should go to 1. Another arrow send me to the state 1. Now I finished 4 arrows going out from state number 0. I will repeat all of this for state 1. Here, layout of the table Q equals to 0 here, Q equals to 1 here. This is actually representing the state. Right. I am in state 1. Will J will K equals to 0s. Where should I go? I have to stay in state 1. 0, 0 here, staying in my state. I am in state 1, JK equals to 0, 1. I should go to state 0. 1, 0 will send me to state 0 as this arrow shows. I am in state 1 and JK equals to 1, 0. I have to stay in my state. Here I have 0, 1. Finally, I am in state 1 and JK equals to 1 and 1. I have to go to state 0. The last arrow here for 1, 1 will send me to the other state. What we have drawn here is called the state diagram for the circuit. I get circuit, get the equation, from the equation get the table, from the table get the state diagram. Now, this circuit is very useful and important, so they build this as a flip-flop. They call it JK flip-flop. Similar to D flip-flop, I would have here the JK flip-flop. They like this circuit a lot because its characteristic will show how useful is this circuit. Give me just one moment here and you will see that. But this is the circuit for this is the J called the JK thesis. They like this circuit, they use it extensively. I need to show the block diagram, I want to show the characteristic equation, I want to show a characteristic table for this thesis. Block diagram is simply a box that shows the inputs. I have two inputs, we call them J and K, and I have Q and Q bar. Characteristic equation of the JK flip-flop, Q plus 1 equals to JQ bar or K bar Q. Right. The characteristic table is usually drawn between the external inputs and the next state only. It should not show the internal input. So that's why we will draw it right here. Okay, we need to study this to drive the characteristic table for the JK. Okay, with Q of T plus 1. JK and Q of T plus 1. Now, how many rows? I have 4 options for the JK. Correct? I have JK equals to 0, 1, 0, 1, 0, 0, 1, 1. For T plus 1, we have the following. So now, if J and K equals to 0, 0, where are those two arrows? Where are those two states? I have here JK 0, 0. I have here also JK 0, 0. Okay. So I want to analyze this. Okay. If Q equals to 0, Q plus 1 equals to 0. If Q equals 1, Q plus 1 also equals to 1. Can I conclude here what should I write for this cell? Yes, definitely, sure. So if Q0, Q plus 1, 0. If Q1, Q plus 1, 1. That means I have here Q. This is, if you still remember the SR latch, this is the case of reading in SR latch. Similar to the read of SR latch. Q. If I have J and K equals to 1, 0, that means this is the second combination here. This and this. Okay? If I started with Q0, I end up with Q0. If I started with Q1, I end up with Q0 bar. So this is similar to SR latch when I have writing. When I have writing. Writing what? Writing 0. Here the output will be simply 0. يبقى ده write 0. Next, I have J and K equal 1, 0, 1, 0. If I'm started with 0, I end up with 1. If I'm started with 1, I end up with 1. So this is the case of writing 1. Okay, this is write 1. In SR latch, we have what's called the forbidden case. Do we have forbidden here? The answer is no. There's no forbidden here. Actually, here, when I have both S, J, and K equals to 1s, which is this case, you see it here, 1 and 1, 1 and 1. If I start with 0, I end up with 1. If I start with 1, I end up of 0. So it is flipping. It's flipping. So I have here the output equals to mean to Q bar اللي هي يسموها toggling. Toggle. This is a very interesting circuit. It's called JK flip-flop. It has the following characteristic table, the characteristic equation, and the design from inside looks like this. If you ever want to use it, you can use it as a flip-flop. Okay? So we will stop here and see you, inshallah, in the next lecture to discuss the T flip-flop and more general circuit for the analysis in lecture number 25, part 2. Thank you.